Copy 724, right. Descend and maintain 2000.
Descend and maintain 2000, 74.
Comment 504, descend and maintain 3000.
3000, comment 504.
In this video we're going to be covering a new section. This is going to be the Pitot or static flight instruments. The first one is like this Pitot or the static system. Like what instruments, we're going to be explaining what the Pitot system is. Basically the Pitot tube which is used to calculate the speed. That's what we're talking about. So what instruments are operate off of this system? So the list is the altimeter, the vertical speed, and the airspeed indicator. The airspeed indicator. These three instruments are using the Pitot tube, or they are part of the Pitot or static system. Now we wanted to talk about this altimeter, right? So how does the altimeter work? So how does the airplane know like what's the altitude of the airplane? So the term here is the aneroid wafers. We're going to be talking about it for the altimeter and a couple of other things here, but wafers. So these, what happens is, we know that the key thing or the key factor which actually changes why is this okay, the key the thing which actually changes by the altitude is the atmospheric pressure change. So there is a, whenever you are going to different altitudes, the atmospheric pressure is changing. So when it changes, what happens is like these aneroid wafers, they expand or contract based on those changes, based on those atmospheric pressure changes. So, and when those changes, this expansion of these wafers or the contraction of these wafers, what it does is like through a shaft and gear linkage, it rotate pointers on the dial of the instrument. So that's how the dial moves and you are aware of your height. So again, this pressure altimeter, again, why it's called pressure altimeter, because it's running off of the pressure, atmospheric pressure. So what are the limitations? So non-standard pressure and temperature variations expand and or contract the atmosphere and raise or lower the pressure levels that the altimeter senses. So what we're gonna be covering here is like this altimeter indication, actually the pressure altimeter indication does vary on like two things. One is the weather, like the temperature, and the other one is the pressure, like the outside pressure. So remember this saying that I'm just gonna write it down for you. High to low or hot to cold, look out below. What it means is like whenever there is a pressure, right, going from high to low, what's gonna happen is like this pressure altimeter is gonna show you that your altitude is high compared to what the actual altitude is. Again, if you are going from a cold temperature uh, to a region where there is from hot to cold, again the same thing is gonna happen. The altimeter is gonna show you that you are actually at a very high altitude, whereas that is not true. So you need to be careful in these two situations. Whenever you are going from high to low pressure region or from hot to cold pressure region, you need to be careful. Again, covering them separately. On a warm day, what's going to happen is the pressure level is higher than on a standard day. So the altimeter indicates lower than the actual altitude. On the cold day, what's going to happen is like the pressure level is lower than a standard day. So the altimeter indicates higher than the actual altitude. Now we're going to be covering some altitudes here. Absolute, indicated, pressure, altitude, true altitude, and density altitude. All of them are very important to know. First starting with the absolute altitude. Absolute altitude is the vertical distance of an aircraft over above the terrain. So being a pilot, if you're looking at the terrain, so the distance of the aircraft from that one is basically the absolute altitude. Indicated altitude, as the name suggests, is going to be read directly from the altimeter, right? Pressure altitude is the altitude when the altimeter setting, like the one which is this indicated altitude, when this indicated altitude is adjusted to 29.92. So when we adjust them into that one, that adjusted um, one is called the pressure altitude. And this pressure altitude is so important that it is actually used for the determining the density altitude, which is we're going to be talking about, and the true altitude and the true airspeed. Now the true altitude is the true vertical distance of an aircraft above sea level. And the last thing is that the density altitude is the pressure altitude corrected to non-standard temperature variations. So that would be the density altitude. Okay, now we want to talk about the airspeed indicator. Again, in the car we have sensors which can actually look at the rotation of the wheel and can tell you the speed of the car. But how do we know, how does this like work in the aircraft where we want to check the airspeed? So it's this indicator, the airspeed indicator, it's a sensitive differential pressure gauge which measures the difference between impact pressure from the pitot head and the undistributed atmospheric pressure from the static source. So it takes two things. One is the this sensor. There's a sensor which will take one pressure from the pitot tube and one from the static port, and would compare it to tell you what's the airspeed, what is your airspeed. And again, the airspeed indicator, what are the limitations? So the limitation is that it is subject to the proper flow of air in the pitot static system. If there is, for some reason, again, if the pitot tube is blocked, you are doomed. Like airspeed won't even tell you anything. So yeah, so again the limitation is that it needs to have the proper airflow in order to uh, tell you the airspeed. uh, Briefly, I wanna talk about this ASI errors. Like what are those? So there are few errors. Like one is the position error, one is density error, one is compressibility error. And position error is the one which is caused by the static port sensing erroneous static pressures. Density error is like changes in the altitude and temperature are not compensated for by the instrument, right? So the instrument doesn't actually, uh, if the altitude is increasing or the temperature is increasing, and that would like, and the pressure is changing because of that, that would not the instrument, the sensor is not gonna be aware of that. And the third one is the compressibility error caused by the packing of air into the Pitot tube at high air speeds. This compressibility error is not an error which you would see in the lower speeds. Okay, now I wanted to talk about, again, briefly talk about some of the speeds. Let's just do 4 here. So the IAS is the indicated airspeed, right? This is the speed of the airplane as observed by the indicator, right? The airspeed indicator. That's why the name comes from, the indicated airspeed, right? CAS, which is the calibrated airspeed, is the airspeed indicator reading corrected for position or like other errors like the instrument error or installation error. So those are the ones. Then the equivalent, this is the calibrated, this is the equivalent airspeed. The airspeed indicator reading corrected for position or instrument error and for compressibility flow, like the adiabatic compressible flow for the particular altitude. So basically this EAS is equal to CAS at sea level in standard atmosphere. So both are the same. If we have the standard atmosphere, the temperature is not increasing, uh, and everything, the pressure is at the sea level, so they're gonna be equal. But the EAS is more like uh, calibrated, I would say, or like it's equivalent to after adjusting for the atmospheric changes. Then the calibrated would become the equivalent. And the true airspeed is the uh, it's the CAS, the calibrated airspeed for altitude and non-standard temperature, the airspeed of the airplane in relation to the air mass in which it is flying. That's the true airspeed. Okay, a couple of more questions here. First, I wanted to just name the some other important airspeeds. Right. Just there is a design maneuver maneuvering speed, and in another video we did talk about this maneuvering speed. Then we have the landing gear operating speed. Again, if your airplane is equipped with a landing gear extension and retention system, you should be aware of that. Landing gear operating speed, it is basically the maximum speed for extending or retracting the aircraft landing gear, right? And then we have Vx, which is the best angle of climb speed, and Vy, which is the best rate of climb speed. Okay, now we have a speed indicator, right? that dial has a lot of markings in here, so we want to be talking about the color coded markings inside that, like the airspeed indicator. Airspeed indicator has a lot of markings, so we're gonna so there is a white marking right at the beginning. There is a white marking. That white marking is basically the flap operating range, like where you can uh, like like mm, like where you the flaps can be operated, right? Then you have the lower limit white arc VSO, that is the stall speed landing configuration. Then we have upper limit white arc, which is the maximum flap extension speed. Green arc normal operating range, and then the lower green limit arc, where the stall speed clean or specified configuration. Then we have upper limit green arc VNO, which is the normal operation speed, and yellow arc caution speed, red line NE never exceed speed. So these are different markings on the that one. Now we want to talk about this. It is very similar to what we already covered, vertical speed, right? We did talk about our uh, we did talk about the altimeter, right? The pressure altimeter. Now we wanted to talk about the vertical speed. So how does it know that like what is the vertical speed of the aircraft? Again, this indicator is a pressure differential instrument. So again, we have this aneroid wafers. They are very much like the one in the airspeed indicator, right? Both the inside of this aneroid and the inside of the instrument case are vented to the static system, but the case is vented through a calibrated orifice that causes the pressure inside the case to change more slowly than the pressure inside the aneroid. So that difference is basically how we know what is the um, uh, basically the pressure, the static pressure becomes lower, and the pressure inside the case compress the aneroid, moving the pointer upward, which is showing a climb or indicating the number of feet per minute the aircraft is ascending. And the last thing I wanted to cover is the limitations for this vertical speed. What are the limitations? So it is not accurate until the aircraft is stabilized. That's what you need to know, that it takes 6 to 7 second lag for the aircraft to stabilize, and then it would tell you that how fast are you ascending or descending. So that is one of the limitations. Those were the things I wanted to cover. Thanks for watching.